In section 4.2.2, you're going to find that solving basic tangent equations is very similar to solving basic sine and cosine equations, except for one small twist. Here's the procedure. To find all solutions to a basic tangent equation, we're going to do the following. Number one, you can probably guess, we need to isolate the tangent function. With the tangent function isolated, then we can apply the inverse tangent function to both sides to isolate the argument of the tangent function. The argument will contain the variable that we're attempting to solve for. Number three, find the smallest positive value on the unit circle that makes the equation true. Then, number four, express the complete solution set as the set of all x, such that x equals alpha that we found on the unit circle, plus any multiple of pi, which is half of a rotation away from alpha. And that's going to be true for all k in z. So notice these look a little simpler than the sine and cosine equations, and that is true. And we'll explore why this is so on example 4. On example 4, we want to find all solutions that satisfy the equation. So the first example is tangent of x equals 1. Notice tangent of x is isolated, and I'm going to solve for the argument by applying inverse tangent to both sides. So we need to evaluate inverse tangent of 1. That is, we need to find every angle on the unit circle with a tangent value of 1. Recall that tangent is evaluated as the y-coordinate divided by the x-coordinate. Hopefully you are already recognizing that tangent of pi over 4 equals 1. And by the way, when the instructions say find all real numbers that satisfy each equation, that's code for radians. So we're working in radians here. So one solution to this equation is pi over 4. And as we learned from the previous video, any angle coterminal with pi over 4 would also be a solution. However, there's another location in one rotation around the unit circle that has a tangent value of positive 1. Recall, tangent is also positive in quadrant 3. Using a reference angle of pi over 4 in quadrant 3, we could easily locate the solution 5 pi over 4. Now here's how tangent equations are different from sine and cosine equations. Recall that we took both solutions in one rotation around a unit circle for the sine and cosine equations, and we added 2k pi to each distinct solution. That is not necessary for a tangent equation. It's possible, but we can do it in a simpler way. If you'll notice, the distance between these two solutions is pi radians, or half a rotation around that unit circle. So we'll be able to express all of the solutions to this equation using that first positive solution, pi over 4, as our springboard, and recognizing that we can add any multiple of pi to pi over 4 to obtain the solution. Now, if I add 1 times pi to pi over 4, I'm going to land at 5 pi over 4. So by adding k pi instead of 2k pi, we are also including the other location on the unit circle where tangent is equal to 1. So tangent equations are a bit more efficient to solve. The set builder notation expression of the solution you'll see is a bit simpler. And that's great news. While it's a little more complicated to find tangent of an angle, solving tangent equations is a bit simpler. Okay, let's try example B. This time we're looking at tangent of x equals -1. So the solution to this equation, x, will be obtained from evaluating inverse tangent of -1. Now let's go ahead and acknowledge the range of inverse tangent. Recall it goes from negative pi over 2 to pi over 2, not including the endpoint. So if we use our calculator to evaluate inverse tangent of -1, we're going to obtain something between negative pi over 2 and pi over 2. So there's a potential of getting a negative answer here, and we always want to include positive answers in our solution set. Thinking of a location on the unit circle where tangent is equal to -1, now if you did your calculator, you would locate negative pi over 4. But we're going to adjust that and make it a positive angle. Notice we could also express that as 7 pi over 4. So once again, inverse tangent of -1 with the calculator would give us negative pi over 4, but we could easily adjust that to 7 pi over 4. Now, we also know that tangent is equal to -1 over here in quadrant 2. We can locate this angle as 3 pi over 4. But once again, notice that our two solutions are pi radians apart. So we can express both of those locations in an efficient way. We can start with 3 pi over 4. I'm going to use the smallest positive angle plus any multiple of pi. That's going to include the 7 pi over 4 stop plus any angle coterminal with either 3 pi over 4 or 7 pi over 4. So tangent equations are pretty efficient. Let's take a look at example C. Tangent of x equals negative square root of 3. Tangent is isolated. We can go ahead and isolate the argument as x equals inverse tangent of negative square root of 3. So we need a location on the unit circle of an angle whose tangent is negative square root of 3. Remembering that inverse tangent has a range between negative pi over 2 and pi over 2. The solution that comes out of our inverse tangent function then would be negative pi over 3. We can easily adjust that to a positive coterminal angle of 5 pi over 3. Also notice that tangent is negative in quadrant 2 at the location 2 pi over 3. In our solution, we'll include the smallest positive angle for simplicity. So we're going to get the set of all x such that x equals 2 pi over 3 plus any multiple of pi to pick up our other solution plus any other coterminal solution. And we have found an infinite number of solutions in this one expression. For our last example, we'll consider tangent of x equals 5, which will not have our common angles from the unit circle as its solution. So applying inverse tangent to both sides, we need to execute inverse tangent of 5. Because 5 is not a common value for tangent on our unit circle, we'll approximate that with our calculator. But I find it helpful to continue visualizing where those solutions are on the unit circle. So let's evaluate inverse tangent of 5 with our calculator. Make sure that you are in radian mode for this. And I'm going to round to the nearest tenth. We get 1 point. Now, if you're not certain where that is on the unit circle, don't forget you can convert it back to degrees by multiplying by 180 over pi. So we're looking at about 79 degrees here. So we'll say approximately right here our radian value is 1.4 radians. Now, don't forget there's going to be an angle over here in quadrant 3 where tangent is also positive. The reference angle is 1.4 radians, so we can find other solutions over there in quadrant 3. If we wanted to express that angle, we could locate it as pi plus 1.4. which would come out to be approximately 4.5 radians. But the first one, the smallest positive one, is sufficient for our solution. So the solution is the set of all x such that x equals 1.4 plus any multiple of pi, k pi, where k is an element of the integers. So these 4 examples show you some potential ways of solving basic tangent equations. All of our tangent equations will whittle down to something that looks like those 4 examples. Let's try example 5, where we have a little bit of preliminary algebra to do before we get to the basic tangent equation. Example 5 says find all angles, so we're looking for all the solutions, but this time we're working in degrees. I don't know about you, but that makes me celebrate a little bit. Degrees are a little easier to visualize than radians. So find all angles in degrees that satisfy each equation. So on example A, the first thing we need to do is isolate tangent of alpha. So let's begin by subtracting 4 from both sides. We'd end up with negative square root of 3 tangent of alpha equals negative 1. Then we're going to divide both sides by negative square root of 3. So tangent of alpha equals 1 over the square root of 3. Feel free to rationalize that if it helps you to recognize the unit circle angle, but it's not necessary because we're looking for the angle here. So I'm not trying to present 1 over square root of 3 as my answer. I'm trying to find the corresponding angle. On the unit circle, we need an angle in degrees whose tangent value is 1 over the square root of 3. Recall that tangent is y divided by x from the coordinates on the unit circle. So if we have a y value of 1/2 and an x value of square root of 3 over 2, we would obtain the ratio 1 over square root of 3. So thinking of the angle on the unit circle with the x coordinate square root of 3 over 2 and the y coordinate 1/2 in degrees would land us at 30 degrees. Also notice tangent is positive over here in quadrant 2 at 210 degrees. But because those are 180 degrees apart, we can express both of them with one simple expression. So the solution to this equation is the set of all x such that x equals 30 degrees plus any multiple of half of a rotation around the unit circle. Instead of 360 degrees this time, it's going to be 180 degrees. Whoops, don't forget, specify k is an element of the integers. And that includes an infinite number of possible solutions to the equation. Once again, distinguish the fact that we have an infinite number of solutions to this equation. It's still a conditional equation. We can distinguish this from an identity equation. We're not saying that every angle on the unit circle is a solution, such as it would be for an identity. We're saying only the angles coterminal with these two stops would satisfy the equation. So there's an infinite number of solutions to this equation, but still fewer solutions than an identity equation. Let's try example B. Notice example B is given in terms of sine and cosine, but we can recognize right here that sine of alpha over cosine of alpha is equivalent to tangent of alpha. So we can write this 3 tangent of alpha minus square root of 7 equals 0. We can isolate tangent of alpha by adding square root of 7 to both sides and then dividing by 3. So we can see tangent of alpha equals square root of 7 over 3. Definitely not one of our common unit circle values. So alpha then can be evaluated as inverse tangent of square root of 7 over 3. Recall that the range for inverse tangent is an angle from, normally we say negative pi over 2 to pi over 2, but in working in degrees, we'll call that negative 90 degrees to 90 degrees. It's important to think about that because I will use my calculator to approximate this answer, and I want to make sure I interpret it correctly. So in our calculator, we're going to flip over to degree mode, if you're not there already, and we'll evaluate inverse tangent of square root of 3 divided by 7. We'll round to the nearest tenth to get 13.9 radians. Oh, hold up. Did you catch that? How about inverse tangent square root of 7 over 3? It's right there to the right of my calculator. I better make sure and type that in correctly. So inverse tangent of square root of 7 over 3 gives me 41.4 degrees. So let's say approximately 41.4 degrees for our first solution. Let's go ahead and acknowledge that tangent is also positive in quadrant 2, and we could locate this other angle by taking 180 degrees and adding that to our reference angle of 41.4 degrees, and this would give us a location of 221.4 degrees. But this one will be sufficient for expressing all of our solutions. So we can say the set of all x such that x is equal to our smallest positive solution, 41.4 degrees, plus any multiple of 180 degrees. And as always, k is an element of the integers. So this expression begins with 41.4 degrees. It includes the solution that's 180 degrees away at 221.4 degrees plus any angle coterminal with those, either in the positive direction or in the negative direction. So this is how we solve our basic sine, cosine, and tangent equations.